Hello. In this video, we are going to examine some further applications of molecular orbital theory to transition metal complexes, particularly those that are octahedral. See this video here to see the general derivation of a molecular orbital diagram for a typical octahedral transition metal complex. We are going to build on those concepts in this particular video. We can divide the molecular orbitals for our octahedral transition metal complex into three categories. One category, which consists of A1G, T1U, and EG symmetry orbitals, these six together here, are bonding. Not only bonding, but they have a large amount of ligand character. They more represent the ligands than the metal. The second category consists of non-bonding orbitals, and that is our triply degenerate T2G set here. This lies entirely, or almost entirely, on the transition metal. Finally, we have anti-bonding orbitals, EG star, A1G star, and up here not shown, T1U star. These are anti-bonding orbitals that mostly have metal character. Recall that the ligands act like Lewis bases. Each ligand donates a lone pair of 2 electrons. Therefore, shown here in blue, we have the electrons that were donated by the ligands. And because there are 6 of them, 6 ligands, we end up with 12 electrons, which means that we entirely fill all of the bonding orbitals with these electrons. Now let us suppose that our transition metal is from the first transition row. Therefore, its valence electrons will be in the 4s, 3d, and perhaps 4p orbitals. Suppose that there are 6 such electrons in 4s and 3d. A typical example might be chromium, which in a neutral configuration, all by itself, has an electron configuration for the valence shell of 4s1 3d5. Recall that chromium is an exception to the general rule. The important thing for us is that we can treat the 4s electron and the 3d electrons as if they were all d electrons. Once we get to the molecular orbital diagram for the complex, we can treat the 4s and 3d electrons as if they were all d's. So in the case of chromium, we have 6 such electrons, which are sufficient to fill up completely the T2G level. Now we notice it's kind of a coincidence that we have here that we can fill up all the bonding orbitals with the electrons that we got from the ligands, and we can fill up the T2G, the non-bonding level, with the electrons that were in the valence shell of the metal. Because of this, it is almost as if we can ignore what happens with the ligands so long as we're in an octahedral field, and we can just concentrate on this region here that involves only the electrons that came from the metal in its valence shell. This is so common that typically when we draw a diagram for the electron configuration of a transition metal, we overwhelmingly leave it to merely this region here and ignore the section that involves the ligands. So here is the electron configuration for just the valence shell for chromium, and recall it as 4s1 3d5. So this is something of an exception to the rules that you are typically taught in school, where you would fill up the 4s before 3d. This is sometimes explained as the fact that the 3d orbitals like to be either completely full, in which case they would be D10, or they would be exactly half full, in which case they would be D5. And this is a particularly stable configuration. In addition to that, a step that many students may find confusing at first is that in inorganic chemistry, we tend to count the 4s electrons and the 3d electrons as if they were all d electrons. So in this case, we would refer to a chromium neutral as a D6 metal. Now I realize that if you look at the electron configuration for neutral chromium when it's not in a compound, that there's only 5d electrons. But it's such a useful trick that as a shorthand, we will refer to it as a D6 metal. To show it as a D6 metal, recall that all these electrons will fill up after we filled up the ligand orbitals, we have these non-binding orbitals, and since we have exactly 6 valence electrons available, we can apply the Altbau principle and fill up the T2G set completely. So this is a typical example of the kind of shorthand diagram that we draw for octahedral transition metal complexes. If we have a neutral metal atom all by itself, all 5 of the d orbitals have exactly the same energy. We say that the d orbitals are 5-fold degenerate because there's 5 of them and they all have exactly the same energy. However, as soon as we make an ion from the metal and or we put the metal into a transition metal complex, something interesting happens, that we get a change in the energy of the d orbitals. We get this splitting so that we get a set of 3 and then a set of 2. And this is typical for the octahedral complex. If we have a tetrahedral situation where we have 4 ligands, we get a slightly different diagram, which we'll treat in another video. How far apart in energy the T2G and the EG star orbitals are is this quantity, delta. Sometimes in the older literature, it is referred to as 10dq. This is called the splitting. The amount of the splitting, the difference in energy between the orbitals, depends upon a number of things, one of which is the type of ligands that are attached to the metal. Different ligands will affect the splitting. Some will have a larger splitting, some will have a smaller splitting. We will look right now at some of the consequences of how changes in the size of the splitting, the magnitude, affect the diagram that we draw for a particular complex. The first situation we will examine is when the splitting is large. In the large case, we call this the strong field situation. A synonym for strong field is low spin. Strong field means that we have a strong electrostatic interaction which causes a wide difference in the energy between T2G and EG star. We will see shortly why it is also called low spin. Let's look at the example for iron. Iron has a ground state electron configuration for the valence shell of 4s2 3d6. Therefore, using the terminology that we have used so far, we would refer to this as a D8 metal. So neutral iron has a D8 configuration. One of the most common iron ions is iron plus 2. Recall that a peculiarity of the filling and depopulation of transition metal orbitals is that we would first remove the 2 electrons from the 4s and we'd leave them in the 3d. So the configuration for iron 2 plus would be 4s0 3d6. And this would now be a D6 metal. Now we want to fill in our diagram with these 6 d electrons. The strong field low spin case is quite familiar in that it is analogous to the electron configurations that you've probably worked with already. First we put in the first 3 electrons and we allocate them this way to follow Hund's rule. And then secondly, we add in the next 3 electrons with opposite spin to satisfy the Pauli exclusion principle. Notice also that we've filled up T2G before we've put any electrons into EG star. You will recognize this as an example of the Aufbau principle. So, the electron diagram for iron 2 plus in an octahedral complex situation would look exactly like this. And we would say this is low spin. Okay. If we figure out what the overall spin here is, each up arrow is a plus half, each one is a minus half, so the overall total spin here is going to be 0. We have a diamagnetic situation. Now let us look at the other case. Suppose now that our delta is relatively small. So therefore we have our iron 2 plus complex, but now because of the ligands it is in a weak field. So now we would have what is called the high spin case. So I will draw the diagram for the electrons for the high spin weak field case. The first 3 of our d electrons are allocated exactly as before. So we see that as far as the first 3 electrons go, whether we're in a strong field or a weak field, whether we're in high spin or low spin, it doesn't affect the first 3 electrons. But now in a weak field, rather than put another electron into the same orbital here, where it would experience a certain amount of electron-electron repulsion, the amount of energy needed to raise it from T2G to EG star is relatively small, so it is actually energetically favorable to put the next electron here. So the 4th electron would go in EG star, and now we continue with the 5th electron, applying Hund's rule again, so it goes there. In a sense, we're finding an exception to Hund's rule. In Hund's rule, we half fill when we have completely degenerate orbitals. Here we're saying, well, if the orbitals are close in energy, they're almost degenerate, so it might be energetically favorable to half fill a slightly higher energy orbital before I double fill the lower energy orbital. That gives us 5 electrons, so I now have one more, and now I go back to the lower row to put the 6th electron. So this is the electron configuration for high spin iron 2 plus D6 configuration. So we notice now as we have, before we had no unpaired electrons, now we have 4 unpaired electrons. So we can determine that this is true experimentally because now we have significant paramagnetism in our transition metal complex. How do we know whether we have a high spin or a low spin configuration? The biggest consideration is the identity of the ligands, which we will look at in a future video, but we can make certain predictions depending upon the ligand, whether it's going to be a strong field case or a weak field case. If it's a strong field case, we're going to have low spin. We want to fill up T2G completely before we go up to EG star. If we have a weak field, we have the high spin case. So put 3 along the bottom, and then we go along the top, and then come back to the bottom. The other important ion of iron is iron 3 plus, the ferric ion. Since we've removed both electrons from 4s, the only place to remove an electron now is from 3d. So now we go from 3d6 to 3d5. And we have gone from d8 to d6 all the way down to d5. With iron 3 plus, depending upon the ligands, we could have either a strong field situation or a weak field situation. So let us first look at the strong field, the low spin situation. For the first 3 electrons, we follow Hund's rule, so we half fill. And now since it's a strong field, a low spin situation, we continue filling T2G till we've used up all the electrons. So now we have the low spin case. Now notice this is still paramagnetic, but this is the lowest possible spin configuration that we can have, being that we have an odd number of electrons. So this would be our strong field, low spin, iron 3 plus. So now let us generate the weak field, high spin, iron 3 plus, D5 case. We know the first 3 electrons go in T2G. But now, because we have the high spin weak field case, we don't go back to T2G, but now we step up to EG. And we have just enough electrons to half fill EG star as well. So now we have an overall spin of 2.5. We have a very paramagnetic situation. So we see that this is the high spin case for D5, iron 3 plus. We can also make some guesses as to whether we're going to have a high spin or a low spin complex. In the first transition row, we have the possibility of both high spin and low spin. Because of the diffuseness of the metal orbitals for the second and third transition rows, because 4D and 5D are very diffuse, it doesn't take as much energy to put 2 electrons into the same orbital. As a result, when we have the second or third transition row as the metal in our complex, those are always going to be low spin. They're always going to be effectively a strong field situation. So we only need to worry about the weak field high spin case for the first transition row, and then only when there are particular ligands involved. We have one remaining topic in this particular video on transition metal complexes that are octahedral, is the idea of the Jahn-Teller effect, or Jahn-Teller distortions. We notice that we have, for T2G, we have 3 orbitals with the same energy, so we say that those are degenerate. We notice that for EG star, we have 2 orbitals, and we say it's doubly degenerate. Now let us go back to the low spin D5 case. So for example, this was the strong field for the iron 3 plus ion. And we had drawn this particular configuration because we had 5 electrons. Now we notice that these orbitals are degenerate. They have the same energy, they're T2G. But we notice that 2 of the orbitals have 2 electrons, but one of the orbitals has only 1 electron. So here we have what's called unequal occupancy of the orbitals. And the Jahn-Teller theorem tells us that whenever we have degenerate orbitals and we have unequal numbers of electrons in them, that the molecule will distort in such a way as to lower the energy. So as a result of the distortion in the molecules, the energies of the orbitals will change. And the orbitals that have the most electrons will effectively go down in energy. It's kind of hard to draw that here, but imagine these have gone down in energy. And the one with the fewest electrons goes up in energy. And the overall result of this is that the molecule now is in a lower energy state than it was before. A good way to remember it is that the ones with the most electrons are the heaviest, so they sink down, and the ones with the fewest electrons are the lightest, so they float as far as energy goes. So this is the Jahn-Teller theorem, and this is a general result which we have to keep in mind when we have transition metal complexes, is that if we have this unequal filling of orbitals, the molecule will distort. It is not always easy to predict exactly how the molecule is going to distort, what the distortion is going to look like, but we know that it must distort, and as a result, the driving force of the distortion is to go to a lower energy state. That seems like a good amount to tackle for our beginning video on transition metal complexes for an octahedral environment. I thank you very much for your attention. Have a good one.